Okay, so we'll start with the sort of the last few slides from the last lecture because we didn't really make it to them last time. So the first thing, or probably one of the most important skills you'll actually learn or develop in your time as a student is sort of the visualization skill. Clearly, you won't learn that much about it in this class, but it's important to cover it because in terms of finding jobs or making careers in academia, making good plots and nice visualizations is by far one of the most important things you can do, and many people struggle with this on a quite regular basis. So it's also quite relevant for this class because it very frequently happens that when you're doing a lot of data analysis or analyzing big data, that it becomes significantly more difficult to do visualization well. So when you look at, thousands of data points or comparing 3D samples or 4D samples over time, you have a lot of data that you need to analyze. And it's quite difficult to kind of just give someone a table and say, look at it. 3D visualizations in particular are quite difficult to compare visually. So when you see two kind of 3D graphs, it's very difficult for you to quantitatively assess, is one bar in this 3D chart higher than the other? And you sort of have this contradictory necessity of you want to collapse your whole result down to one single simple value, but you don't want to lose any of the important data involved. And so you want to get rid of all the noise, but you don't want to cut away any of the signal. So the first thing we'll kind of go over, where we just have a few simple examples of this, is bad graphs. So there's way too many graphs, and if you've been to scientific conferences or read papers, I would say a majority of graphs tend to fall in this category, which say my data is very complicated, or worse, I know how to use this random toolbox in MATLAB R or Mathematica. And so that when you have a graph like this doesn't really tell you anything. You could simply have a sentence, the data is very noisy, and that would be fine. There's no trend you can perceive here. It's just quite a mess. Similarly with this, which I think I saw in a presentation not that long ago, what is that supposed to show you? That all the data is mixed together? You can use a nice sentence to say that. You don't need to use a plot to say all the data is mixed together unless you have something you're actually trying to show. And so, just putting the data into your plotting tool of choice and trying to export it isn't a good way to try to visualize it. Good visualizations take lots of time. And, here's another example. You see it quite frequently in genomics, which is why we'll have a couple slides dedicated to that afterwards, where you just show huge complicated networks, and they might be fun. I mean, they could be interesting as like an artistic rendering or something like that, but they're certainly not valuable to help you understand the data better. I mean, here, even on these simpler analyses, what is this plot supposed to show? You could look at this plot for hours and still not really be able to say anything about how these values relate to mice, which are in the middle, and then how mice relate to human. All you could really say is there seems to be lots of random connections everywhere. There isn't any additional information by showing this plot in this way. And so kind of the key ideas is sort of what is your message? So what are you actually trying to communicate? So much like you learned in high school or grade school writing classes, if you try to write an essay, the first thing you have to come up with is the thesis. What is your goal? And not just start writing random words, which is what a lot of these plots are. Does the graphic communicate that clearly? So does someone who looks at your plot see that message that you're trying to get, or are there 30 other messages that they see at the same time? Is a plot even necessary? So in many cases, using plots isn't really helpful to visualize what you're trying to show. And just saying it's very noisy. And then the last part, which comes from Tufte. Has anyone heard of him before? Oh, just, okay. Well, one person's already good. Says every line and color serve a purpose. And so if you pretend ink is very expensive, You don't want to be using lots of ink if it's not showing any information. So these were the slides that were mentioned at the beginning, and this is sort of relevant to genomic data, but it fits quite well for other big data, and of course the slides are much nicer put together than mine are. But yeah, here's the first graph, which I think is probably the justification for this, is that sort of what are you supposed to see in a picture like this? And their own examples of bad graphs and the citations associated with them so that you know that it actually came from real papers. And so kind of the rules that I've simply copied from this was sort of, is it necessary? What is your message? And does my figure communicate it clearly? So, that someone else is immediately able to understand it. And are there extraneous or ornamental elements? So of course, if you're working on a marketing brochure, you don't necessarily need to apply all of these rules. You're trying to make something that looks cool, that people get excited about. It's a very different task. But as a scientist, your goal is not to make something that looks cool. Your goal is to communicate clearly what you've done, and that someone else can take that and turn it into this marketing garbage. But that your goal is really to be focused on how do I make a graph that best communicates what I'm trying to do. And then sort of the last part is, have I left the reader wanting more or less? And so does the reader understand the graph enough to kind of be interested and ask questions? And are there lots of things that the graph kind of brings up but doesn't answer? But that, the rule they sort of have here is, in terms of quality of communication, the first thing is really that you need it to be legible, so that, if you're making it, you need to be able to read all of the fonts. You need to be able to read all of the text. The text can't be overlapping. The text can't be hidden behind other things. The legibility is really the first level of making a good graph. The next part is clear. So are the trends that you're trying to show or the message that you're trying to get across very clear, and that the last step is attractive. And so you really need to build up in that way, rather than starting off with making a really, really cool looking plot and then trying to figure out how to make it legible and clear afterwards. So lack of a clear message is one of the biggest problems. Here's a fairly good example of a clear message. There's not really many ways to interpret that sign. It's quite obvious. And that here is kind of the trajectory you should be taking. So you start here, first legible, then clear, then pretty. And so info horror, this is one of the graphs that that I find particularly bad, that when you're here, you very clearly started with making it pretty. So some random toolbox that this person was working with had a 3D cone chart plot, and you can now look at this data and see that it's actually quite difficult to compare the heights of these different elements. That 47% appears a lot less than 62%, and 87% appears almost the same as 95%. So that your quantitative assessment isn't really related to the size of the cones that you're looking at. And so when you're trying to assess something, here the height of the cone represent that percentages, but what you interpret as a reader is the volume of the cone. And so of course with a cone, the volume sort of gets smaller and smaller. The incremental volume gets smaller as you get closer to the top. And so this makes it very difficult for you to quantitatively compare these things. Now, again, if you're on a marketing perspective and you want to minimize differences between 82% and 91%, then this is probably a very good chart to do. If you want to say, I have a model and it gets 82% accuracy, this is probably one of the best peaks to use for 82% accuracy, because it looks almost as good as 100, even though 82% is quite far away from 100. But it's very bad at communicating what you're actually trying to communicate. So parsability is kind of one of the big things, then some more graphs like we had before, and sort of helping the reader identify meaningful patterns. So that's one of the key elements of sort of the parsability. And if no patterns exist, the figure is not necessary. So you don't need a figure to say there is no pattern between these two lines. that's not helpful. Showing this plot, it's of course very impressive that you know how to use this tool, that you can read the data in, that you can make this thing, but it actually doesn't communicate any information. And so it doesn't belong in a scientific presentation because there's no pattern you're trying to get across. And just saying it's complicated is not sufficient. Similar, I think, there is no emergent pattern. This is completely unparsable. For you, of course, for yourself, when you're visualizing your data, this can be very helpful to come up with, there's no clear pattern in this data. We don't need to analyze it further, but there's no reason you would need to publish this graph or use this graph in a presentation because it's not useful. It's not showing you anything. And it also doesn't prove that there's no pattern. It just proves that the way you chose to look for a pattern didn't find one. And so it's kind of a negative result, but it's not a particularly useful one. And so what you kind of want to have is, an emergent pattern in the raw data where you need to sort of show all the data in order to get that pattern out. And so in this example, you have lots of kind of random little things, but the picture of the person comes out when you show the raw data. Resolution is one of the other major aspects of legibility where, your chart has to be legible. And if you have graphs like this, where you have little micro tiny points and very tiny labels, it becomes very difficult to figure out what's going on. It then becomes even more difficult if you take this, orange point here and try to figure out, does it belong to 13, 14, or 15? People are clearly not computers, and giving a chart like this, particularly when this is referencing genome, so if it's on 13 or 14 or 15, that makes a huge difference for how you interpret it. It's not kind of an arbitrary measurement. And looking at a graph like this makes it incredibly difficult. And so the kind of legible limits, so here are just sort of a few examples for, if you're reprinting on paper or if you're printing, if you're doing a presentation, how small different lines can be in order for them still to be seen. And I will be the first to admit I don't follow all of these rules myself. It's quite difficult to follow all of them, but you should at least be aware of them. Color. This is one of the critical problems we run into a lot, is that we don't perceive all hues as having equal brightness. And so if you are making a bar chart or a scatter plot and you use blue and yellow as your two colors of choice, the yellow appears to be brighter than blue. So when someone looks at your chart, they're going to be drawn to the yellow points rather than the blue points, which isn't what you're trying to do typically when you're making a scatter plot or a bar chart. You want to kind of show all data the same way. And so so if you show this plot here, these are, 3 species of whatever, and you have these charts, and of course the yellow is the only one you look at. And the yellow was not intended to be the most important one. This person just wanted to have 3 different colors shown. And so using colors that don't have equal perception make it very problematic for someone to kind of read your chart in a normal, unbiased way. And so here, using yellow was a very bad choice because you didn't want to necessarily command attention to that one species when all 3 of them are equivalent or at least on the same level. And so this is where we get back to that color diagram we mentioned earlier with the sort of HSV, where you can sort of have perceptual uniformity. And so you can try to focus on colors that are all perceived with the same intensity and, saturation, hue, saturation, and value, I think. And that there's lots of color schemes that build this in. So has anyone heard of the Brewer color scales before? So I think they're part of Matplotlib or Brewer color palettes, where that they're palettes that are built to be uniformly perceived. So colorbrewer2.org, where you can choose all of these which have the same perceived sort of intensity so that nothing stands out. And so a lot of tools now incorporate this so that you can make plots that look that are perceived uniformly. Whereas, a lot of the original tools that came out, or if you look at MATLAB, they have JET, for example, as one of their default. So here, this blue to yellow to black is what is the default way it shows intensity images, for example, in MATLAB, and that's perceived all very differently. And so when you're trying to look at the image, it becomes very difficult to see differences because there hasn't been that normalization performed. And so there's more examples of what this looks like, how to choose colors. Also tools like Adobe have spent a lot of time coming up with this because they want to come up with palettes that make sense and where things are perceived correctly. So clearly there are ways to optimize this, if you really want to command attention to one part of your data set. But in many cases, you're just trying to show many different things and you want to show them as equals. And you have all of these palettes you can look at to get more information on that. Visibility, sort of the next one, where having a yellow background on this adds no value. It's also kind of a waste of ink and makes it more difficult to print out or see the sort of different barriers inside it, whereas having sort of just black and white makes it a lot easier to look through the plot. Similarly, if you're doing black on white, if you work in a hospital in radiology, you might be more comfortable with that color scheme, but for everyone else, it's significantly easier to see and view the plot in this sort of standard view. Similarly, all the points, here where you don't show anything with color and here where you show things with color, you get more information. It's still probably not a good plot, but at least it's much more insightful with that. And then finally, is scatter plot actually the best way to show all of your data points? And here, sort of having 2D histograms is a much better way to actually visualize the trend in your data, so that once you see there's a huge number of points here, it's very difficult to perceive how dense the points are. And so, for example, this area appears to us just as dense as this area because the points are plotted so large that you can't really tell the difference between them. And when you use a 2D histogram or a density plot or a contour plot, you're now able to see that the density in this area is much higher than the density down here. And that you can change the size of the bins to get sort of tweak the plot to look how you want, but that this plot doesn't help you communicate that. And so in many cases, showing all of the data points is sort of a complete overload for what you're trying to present. And here again, you can have contour lines and other trends to kind of show, rather than plotting every single point, you can show the contour and then you can show like a linear fit. And so this gives you an idea of how the density of the data distributed and sort of what are the correlations between those two things. And so there's really a lot of opportunity to make plots better and easier to read and more sort of quantitatively understandable. So yeah, the reader's not a computer. Again, you've probably all seen plots like this, where you have all sorts of charts, and what anyone is supposed to do with all this information, I don't really know. It's impressive they collected it, but again, it's not particularly useful. Here, again, what you're supposed to do with this, how are you supposed to interpret this, what is the message of any of these plots, it's very difficult to say. And when you start showing tons and tons of data like this, it becomes very difficult for someone to look at and get a good feeling of what's going on. The only time these plots are very helpful is if you were to look at this plot, for example, you would see that there's these lines here that form. And so that would be, as someone analyzing the data, useful to show, because then you could start thinking about, why are these lines coming up? Is there some sort of rounding error? Is there some sort of quantization? Is there a mistake in my tool? Am I counting things incorrectly? And that would be then a useful plot to figure out that something you've done might be incorrect. But to help someone else visualize the data, it's not a helpful plot at all. Yeah, so text orientation, we won't go through the rest of this, but there's lots of good examples here. The last thing, which is kind of important to say, is that there's almost never a situation where this plot is an appropriate plot. So 3D plots are almost always bad, particularly if you're not showing 3D data. And so if you're showing, what you could easily be showing with a 2D plot, then there's no reason to use a 3D plot for it, because you have this whole perspective change, and it becomes very difficult to tell, how much is the difference between this value and this value. And is this here, is it closer to 0.2, is it closer to 0.1? And looking at this chart, you'd have no idea. And if you plotted it on a 2D plot, it'd be very easy to say that. And so there are lots of good ways for transforming things from 3D to 2D. But in general, yeah, you don't need to worry about them. Yeah, and the last one is sort of junk, where, adding ridiculous, infographics to your plots doesn't really add value, and certainly makes it a lot harder to actually see what's going on. So these charts are certainly pretty. They might be interesting if you were making, an advert. They're not interesting if you're a scientist. They make it a lot more difficult to see the trends that you're trying to get across. And so, yeah, so I think we'll stop there, but there are lots of slides there. I think it's helpful to go through it, and at least something to give thought to before you make plots, because it's something you'll be doing probably the rest of your career. The only last part of this that I'll mention is there's this idea of sort of the grammar of graphics, where you kind of have a set of rules for constructing, in English you have a set of rules, or German, for constructing and validating a sentence. So is the sentence grammatically correct? You have a subject, a verb, and an object most of the time. And the grammar kind of lets you say this is correct and this isn't correct. And if you see a sentence, you know how to parse it. You know how to say this is the subject, this is an adjective talking about the subject, this is an adverb talking about the verb, this is a preposition. These are how all the things are linked together. And so what people have spent time doing over sort of the last 40 years are working on things called sort of the grammar of graphics. And so how can you make a plot interpretable in the same way that you have grammar in sentences interpretable? And so there's, important books about this, where you have sort of discussions about what are the grammar of graphics. And one of the most useful tools for this is an R library called ggplot, where you then are able to actually apply this quite easily. And so if you go to grammar graphics, there's a number of books you can get about this, and that you can look at Hedley Wickham's original paper on this, which is preprint. Kind of how do you build up a plot from sort of, what are your data, what are your axes, what are you trying to show on top of it, and how do you kind of layer these things together? And what makes this a lot more understandable or applicable is that there's actually a library he's built on top of this to actually build charts in this way. And so you can take very, very complicated plots and map sort of data to the sort of the defaults, the transformations to how you map the data onto the plot, the elements, the scale, the guide, the coordinates, and then you end up with some examples down here. Yeah, where you have these ideas of making a plot, adding the data, adding the transformations, adding the scales, adding the coordinates, and that you kind of layer your graphics in that way. There's also a lot of Python tools that have started to take this approach as well, where instead of thinking of you have one plot command, that you have a number of different things that you can combine in different ways in order to build a plot just like you would build a sentence. And so it's very helpful for making good, clear plots and sort of making things consistent. And if you use these tools, it's quite easy to switch between different kinds of plots. That one of the problems you run into when you do things in sort of MATLAB or even Matplotlib is that you have different commands for making a log scale versus a linear scale, and that it becomes quite difficult if you're making a certain type of bar chart and you decide afterwards that you want to make it on a logarithmic scale, that you have to kind of completely start over. And with this, you just sort of add a logarithmic transformation as one of your layers in your plot, and then it gets applied whether your plot's a bar chart or a tile chart or anything else. And so there's some examples in this, and it's potentially interesting to go through. And so yeah, wrapping up for the last lecture, again, this is not a statistics course, also not a visualization course. There are many good courses on visualizations and statistics that you should probably go through. If you have questions or concerns with statistics on a particular project, both ETH and University of Zurich offer free consultations with real statisticians. So if you have actually a data set and you're unsure if you've analyzed it correctly, you can go to them for free and talk about how you collected the data, what your hypotheses were, what you're trying to do to test it, which tests make sense, how you should correct for multiple testing, and they can kind of help you improve significantly with people who have a lot of expertise in the field. So I would strongly recommend doing that for anyone who gets involved in more complicated problems or has a feeling the tests, the simple tests, aren't applicable. And because it doesn't cost you anything, there's no real harm. The only kind of downside is that they are rarely sort of bearers of good news. That if you talk to the statistical office, very often they'll say that the conclusions you've drawn aren't justified by your data. And so they'll sort of bring down what appear initially to be very exciting results to somewhat interesting results. And that they will very rarely tell you, look at this super exciting thing that you've completely missed. They're much more likely to tell you, the thing that you found actually isn't really valid because the way you performed your study doesn't let you make that assertion. But it's still helpful because it helps improve your process and make sure that the work that you're putting out sort of has the rigor that you would want to have in larger studies. So, are there any questions on that? Okay, so we can